Welcome, everyone. Iberamia 22 is presenting a series of pre-events with up-to-date researches in artificial intelligence. Today, we have the pleasure to receive Professor Luís Correia for a talk. Cristina will introduce our invited speaker. Hello, Cristina and Professor Luís.
Hi.
Thank you, Marisa. So it's before introducing Luís Correia, let's just remind you that Iberamia 2022 is going to be in Cartagena de Indias. It's going to be November 23, from November 23 to 25th. And I hope I can see all of you there and you can join us for a very nice get-together to discuss new artificial intelligence techniques, but also to create a community, a Latin American community with Portugal and Spain. So it's my great pleasure to introduce Professor Luís Correia. Professor Luís Correia is right now is a full professor at the Universidade de Lisboa. I've seen Professor Luís Correia for a long time, more than 20 years. And it's my pleasure because he will bring a new perspective on what we have been talking about in our pre-events. So he has been working bio-inspired algorithms, but today he's going to talk very specific about the importance of context in AI reasoning. And it's also can be seen as a way to combine symbolic and sub-symbolic reasoning. And this fits very well with our trend, our AI trend that we need to improve and to make artificial intelligence more a broader scope, but also to provide explanations and to be able to be audited for some unfair decisions. So it's my pleasure to introduce Luís Correia. Please, the screen is yours.
Thank you, Cristina, and thank you for inviting me for this talk. As the title and Cristina mentioned, I'm going to talk about the importance of contextual knowledge in artificial intelligence. And let's start by a very simple problem that is presented in AI 101, an abstract problem that is a search problem to find a way from a starting point A to a goal G, not knowing where the goal is. Okay, and this is a problem. As you can see, there is very little information. So we basically will have an artificial agent looking with the equal probability in any of the directions, supposing that the agent has to go through the grid that is signaled here. So we don't have any further information, and we're going to see the agent do a problem of blind search. And in fact, it's blind because the computer or the artificial agent only knows local information and what it has already explored. The local information is what is accessible, and I represented it by these you can see my mouse, yes. These lines, black lines here, meaning that has a radius of 1 to see the next, let's say the next crossing or the next node in the chart. Okay, and it has memory, so it has a memory of what it has already explored. But we have to realize that we as humans, when we don't really solve such a problem, usually we have more knowledge, and the knowledge that we have in the first place is we know that this is a grid world. We expect that this problem is solved with perfect action. So with a movement, if we decide to move from node 1 to node 2, the agent will move. so perfectly. We expect that the neighbors are detected very well so that we can know what is the next neighbor in each directions without errors. So these are perfect perception and perfect actions. And we also know the overall dimension of the grid. And all of this is important because it implies that we get to know if the problem is feasible to solve in the first place, something that the agent doesn't even have a clue to do that. In fact, we as AI practitioners will only start an artificial agent to solve this problem if we know that it is feasible to solve. However, let's suppose that we can give the AI agent a little more information. In particular, we can give it an heuristic that is an estimate of a distance from the current point where the agent is to the goal. And at this point, it's basically similar to deforming the space, favoring what is the estimated direction of the goal. Basically, that's what the heuristic does. So suppose that we want to go to the goal, and the way we have the heuristic basically tells us that to go in this direction, we move a space that suppose that is this distance in the grid corresponds to a space, we move closer to the goal. Okay, while we moving here, we do only a small step towards the goal. You see, basically it's the equivalent of deforming the space. And in fact, we know that the context is the more context knowledge we have, the better is the heuristic information quality. So, for instance, the better heuristic means that the search is more efficient. And if we assume that we use the most efficient possible way, this type of heuristics in a grid environment, such as the A-star algorithm, then we know that the most efficient search is the one that expands less nodes, where the agent has to expand less nodes. And we can measure, in this case, we can measure the heuristics. The best heuristic is consistent and dominant, meaning consistent that it respects the triangular inequality. It never overestimates the cost to G, which is admissibility also. And dominant, meaning that the estimate of that is done is greater or equal than any other estimate that is compared to this one. And that's how this heuristic is dominant. And these are important features that we can analyze briefly in a diagram. For instance, if we don't have an heuristic, the agent doesn't know the space, blind search. It basically has let's suppose that it has this radius of observation. The goal is outside the radius. The agent doesn't have a clue in which direction to go. By providing her an heuristic, some heuristic, we get a deformation of the space towards the goal. You see that there is a favoring the progress of the agent towards the goal. And in fact, if we have a perfect heuristic, then we realize that there is no extra node that is explored in searching for the goal. So we know that the agent is doing the best possible search to reach the goal. And this, in fact, the perfect heuristic is called an oracle, meaning that someone gives us the solution, let's say. Okay. And for instance, let's say we have a map. Okay, we have signaled here the starting point A and the goal G, and we want to plan a way to go from A to G. Of course, we can plan it by walking or bicycle or car, etc., depending on what we want. But let's suppose by car, the white lines represent the roads, and so we can make a plan. And of course, we all realize that we look for intersections, and we try to find out the shortest path, etc. But now let's suppose that we have more information, so more context information, for instance, having the traffic signals. So we know that the streets that we have here. Some of them have, for instance, this one only goes in this direction, this one only goes in that direction, etc. And here the same thing. Some of them have limited directions. So this gives us much more context information, which allows better heuristics. In fact, by having this information, we can exclude paths that we would possibly have signaled in the first place without this information. So in fact, we in the first one, without this context information, we would have could have planned infeasible paths in the real environment. And we can I can go on with this. For instance, we can improve this heuristic if we have current information of workings in the streets, in the roads that are here. Okay, suppose that the county the council is doing some improvements or correcting something, and a street is closed, and of course this is further context information that we have, and we are quite used to this. If we live in a city, we know have a lot of context. If we go to another city, we visit another place, we don't have this context, and usually we resource to now the GPS tools, etc., etc. We may have a similar situation in games. For instance, in chess, it is used by human players and by artificial players. Heuristics are used, and they to improve the quality of game. And the heuristics get better with growing knowledge of game strategies. So, for instance, even if you don't know how to play chess, you know that there are different pieces in chess. The P stands for pawn, the B for bishop, the N for knight, the R for rook, and the Q for queen, and of course the king, which has an infinite value, because the king is, if you lose the king, if the king is captured, you lose the game. So there is a simple heuristic that players use that says that pawns have a value of 1 point, bishops have a value of 3 points, so have knights, rooks have a value of 5 points, and the queen has a value of 9 points. This has to do with the capabilities of movement of these pieces, and this gives us it gives the player a kind of a degree of importance and of protection that the player should use in playing to protect these pieces, and of course he is more likely to lose a pawn to preserve a rook or something like that. And the same thing if the player is going to attack pieces of the adversary, is going to prefer to attack high value pieces. Okay, so this is a kind of a simple heuristic. Heuristics can get better, but we need to know more about the game. And for instance, another one that is common is the pawn structure. And this becomes more difficult to evaluate. Of course, expert players do that very easily. For initiate players, it's more difficult to understand if a particular pawn structure means that after playing some moves, the pawns have moved, your pawns have moved, my pawns have moved, and we can the players can evaluate the pawn structure of each one, and the pawn structure. There are good pawn structures and not so good pawn structures. So and again, it's more difficult to establish a value. Of course, there are rules for that, but it becomes more difficult. And the third one that I'm showing here is the piece positioning in general. So you can look at all the pieces, and we have each player has 16 pieces in the beginning, and we 8 pawns and 2 of any other pieces except the queen that is 1 and the king that is 1 also. And the way they are positioned in the beginning is identical for each player, and then we start playing, and we move the pieces, and again the expert players can look at the overall piece positioning of each player and can evaluate and say, okay, this is a good positioning or it's not so good position. So you see, we need more context for this type of evaluation in chess. And this was the type of information that was used by by this computer on the right, the Deep Blue, that in 1997 beat the world champion at the time, Garry Kasparov. And it was a machine that used a lot of heuristics, had a huge database of played games, so it could use this information, but it didn't use any type of machine learning. Okay, so these were rules that were developed and input to the machine, and it didn't use machine learning at the time. Okay, we'll get back to this, but I want to go over a few problems, a few areas of artificial intelligence to exploring this idea of the context information. And another one that we use, we have and has some similarities with the real world. For instance, is suppose this scenario when we want to reach the peak of the mountain. Okay, well, we don't see any predefined trail, so we can go wherever we can walk, let's say, but we should have some measure of performance. How well are we doing? And a good heuristic is the altitude. Okay, we want to reach the peak, so the higher we are, the better the closer we are to the peak. Supposedly, if we go in the direction of the peak, of course. But this may not be consistent in the sense that, for instance, representing this type of heuristic as a function, we could, using this function f of x, we could obtain a gradient, which means how does this function vary? How does the height vary? Okay, and if we go in front from that position the image was taken, we know that we are at some point we should start to climb, so to get higher. Okay. But this might not be very useful, especially if we have what are called rugged landscapes. So landscapes with this type of aspect. Okay, so if it's a smooth landscape, then we are sure that if we go into the direction of the peak, that we will eventually reach it. Okay, this one is not so bad. So if we go into the direction of the peak, that's the same thing, because there are not much irregularities in the height. But this one, we start to move into the direction of the peak from this point, let's say, and we reach this intermediary peak, and then around it, we don't have any higher peak. So our measurement, if we don't see far away, our measurement tells us that in the vicinity we have to go down, and so the heuristic measure is not consistent anymore if we don't have a long vision, range of vision. Okay, so we see that, and this is a problem that in artificial intelligence, in general optimization problems, we have to envisage the possibility of finding an arbitrary landscape. So we don't know if the landscape is smooth or if it's rugged, if it's regular or irregular, etc. And therefore, we need to design a method that establishes a compromise between speed in following a gradient, because the gradient we follow can you confirm? Okay. And the quality, which means to find the optimum or reach what is called a kind of a local maximum, meaning a peak that is below the quality of, or below the top of the mountain that we wanted to reach, the quality of the highest point. Okay, and this, in fact, is expressed as the compromise between exploitation and exploration. So the exploitation is to try to reach the highest peak that we have nearby, and the exploration is to look around to check if we have peaks that are higher than this one. And this is a general problem in optimization and in machine learning in general, that to be solved requires, or to be better solved requires contextual knowledge. In particular, for instance, the type of landscape. By knowing the type of landscape, we can configure the exploration or the algorithm that we use in a way that is more adequate to this type of landscape. And there is, in fact, a very nice work called the no free lunch theorem that is applied to this, meaning and say that showed that we don't have an algorithm that is the best one in any type of landscape or in every type of landscape. So, and basically, if an algorithm is very good in one type of landscape, then it is going to perform very poorly in some other types of landscape. And this brings us to another aspect in artificial intelligence that now is machine learning. And I'm starting with reinforcement learning in particular. And why did I choose this? Because reinforcement learning is a modality of machine learning where the agent learns to solve a problem involving an action of the agent in the environment. And the agent learns to solve the problem with little information, very little. And in fact, along the way, this type of machine learning is characterized by providing only a reinforcement signal, an occasional reinforcement signal, in fact. And the reinforcement signal can be something very simple as you're doing fine or not, you're not doing fine. And being occasional, it means that this signal is not provided after every action of the agent. It can be provided after some actions, after reaching some point, etc. Okay, so basically the agent keeps observing the environment, the state of the environment, deciding how to act upon the environment, which changes its position in the environment and may change the environment itself, and keeps doing this until it at a certain point receives a reinforcement signal, and then decides, possibly changing its internal policy, and decides what to do next. Okay, and for instance, I'm giving here some reinforcement signal examples. In a chess game, could be the result of the game. We have 3 results possible in chess: win, loss, and draw. Okay, so typically we use as in chess, it's used. Win is +1, loss is -1. In chess, in fact, win is 1 point, a loss is half a point, is 0 points, and a draw is 0.5 points, 0.5. In a navigator agent, the reinforcement signal could be the length of the path. So it tries to find the shortest path. And in this problem that I illustrate here, the robot balancing a stick, the reinforcement signal could be only the stick fall. So if the stick falls, we get -1 of the agent gets -1 of reinforcement. Otherwise, it doesn't get any reinforcement. So you see that the agent has to learn with very little knowledge. Okay, and basically it's a problem of trial and error to solve this. In fact, this is a formal presentation of the way this is expressed in mathematical terms. But basically, the important thing here is that we have a set of states that the agent can observe, a set of actions that the agent can perform. These actions may be limited, so some actions may not be possible in some states. There is a reinforcement function that the agent receives occasionally, as I mentioned. And this is very important, is the policy and the value that the agent obtains by the actions. This is solved or can be expressed as a Markov decision problem that is to maximize this value that is dependent of the policy. This value is the expected value of the sum of the reinforcement over time, over iterations. Multiplied by this, that is called the discount factor. That means that is applied so that the agent can wait for some reinforcement in the future and not be too much drawn away by the current reinforcements or lack of them during the process. Okay, and this policy is expressed here in general terms as a stochastic policy. So we have some probability of in state S. Okay, and this the policy basically makes the agent search for the or the reinforcement learning policy is to choose the optimal policy so that when it is the agent is put in an environment, it finds the best sequence of actions to reach the goal requires the training requires many episodes, a lot of random search with not only because at a certain point the agent starts to know what is the best action in some point, or the best action that it knows at that point, but we still it could be a under par action, so an action that is not the best one, in fact, that is better than some others that the agent tried, but is not the best. So this epsilon greedy policy allows the agent to explore once in a while some other actions randomly, so that it can find see if it can find a better action. So again, this is a problem where there is a need, a balance, or a compromise between exploitation and exploration. And this happens because usually in these problems, in reinforcement learning, the agent has little information about the optimal policy for action sequences, and this is very different from what we see in animals and especially in humans, because again we have a lot of contextual information. And currently, recently, we see that better results in reinforcement learning have been found with approaches typical of optimization to find the optimal policy. So heuristics for meta heuristics, some of them are bio-inspired, and with some other heuristics, in this case involving domain knowledge or offline data. And here, the optimization, as I mentioned, with evolutionary algorithms, so bio-inspired algorithms, where the fitness itself can be used as a heuristic. And these are quite recent results, and they have state of the art in reinforcement learning problems. Let's see another aspect of context and of of course the importance of context in artificial intelligence is not new. It's something that is known for a long time, but it's important to see efforts that have been done and how these are integrated in nowadays solutions. And as we have seen here, in this case, in reinforcement learning, is still to try to do the best we can in this first paper of Choromansky and colleagues. It's to use bio-inspired algorithms that do surprisingly well. Well, at the time it was do surprisingly well in finding an optimal policy, or we have domain knowledge or offline data, which amounts to the same, to have more knowledge of more contextual knowledge to help the reinforcement learning problem. If we want to talk about context in general, the SITE project is a very interesting project that started in 1984, where Doug Lennart, the responsible researcher for the project, had the goal of creating a computer with common sense. Okay, and therefore he started defining an ontology and filling this ontology in this system. And the Psych project in 1986 had an estimated 2,500 rules and 300 person year to solve it. Let's say to create this system. This estimate was passed, and in the first version in 2002 had already 6,000 concepts and 60,000 facts. And 10 years after, in 2012, it had already 239,000 concepts and over 2 million facts. And currently it is connected to the Wikipedia and some other sources. And actually there's a version online, and you can contribute to the open site. But it's interesting to observe that, it first has one limitation: it doesn't evolve by itself. So all the rules are input by the humans, and it's not embodied, a problem that we'll cover shortly after. And everything needs to be described. This is von Pratt in 1994. He analyzed the psych, and it says, well, psych knows that soup comes in 8-ounce quantities, but it doesn't know that you die without food. Again, a lack of context and relating knowledge. And for instance, when drinking a cup of coffee, you hold the open end up. You see that these are, and you can't be in two places at the same time. These are, this knowledge is so common that we don't even realize, we don't even pronounce it. But it's a lot of knowledge that we end up acquiring from birth, right? From when we are born and observing the world around us and practicing in that world, etc. Okay. Now let's look a little bit at some AI without heuristics. Okay, and in particular, the highlight is deep learning, where we don't have any type of heuristics. But we see that deep learning requires, in solving problems, it requires an enormous amount of training examples, and does not produce human interpretable symbolic knowledge. Okay, so yet we should realize, and I'm going to make a parallel here along the slides that are coming afterwards now. We also learned how to ride a bicycle, and we can't express it symbolically. It's not easily describable, and even if you can express it, it is not of much use for the person that is trying to learn based on that explanation. So it's basically useless. However, there are very impressive feats of deep learning. For instance, the AlphaZero system that was created by Google. It learned Go, which is a board game, also an Oriental board game, Chinese and Japanese, chess, and shogi, that is an Oriental kind of chess game also. So we learned these three games by playing against itself, using reinforcement learning and deep learning. And in 24 hours of training, it outplayed the Stockfish, which is a standard state-of-the-art software for personal computers playing chess, and the Elmo, a similar one, a software that plays shogi. And a previous version of the AlphaZero, that was AlphaGo Zero, of 3 days. The AlphaGo Zero was limited to playing Go, and was the program that beat the world champion that was in the news, etc. And you see that we are already talking about very powerful machines, like 5,000 TPUs. So the TPUs are tensor processing units that are very fast CPU types that process tensors, basically matrices and vectors that in higher dimensions. And these of the first generation, and 64 TPUs of the second generation for the neural net training in parallel. Okay, so these generated games, and the other part was used for the training. And more recently, the Google also produced the Mu-Zero in 2019 that extends the superhuman performance to 57 Atari games. So these Atari games are like games that move, that you play with a joystick, etc., etc. So this software was able to achieve superhuman performance. And in all cases, we can say, okay, these are very specific contexts and very limited with a very well-defined space and rules. Okay, but we see that deep learning with achieved state-of-the-art results also in a variety of large size problems, and large size means many features and many examples. In particular, classification problems, either static tabular problems, so classification in general, time series problems, artificial vision problems. However, it's deceivable, and we have, in spite of having these very good results, superhuman results, so performance better than humans on average in these problems, we see that it can produce catastrophic fails. So basically, small catastrophic fails mean that small perturbations can produce huge errors. And this is an example from this Sayed Mohsen and colleagues paper in 2017, where a system was trained to identify images, and so it correctly identified the original picture as a joystick, and then the image was perturbed with some noise that is this image behind here, and you see that the resulting image is kind of similar to the first one, except with a little bit more noise. Okay, so it's perturbed, but for us it's not a big difference. But the classification system now produced as a classification a Chihuahua. Well, and if you do not realize what a Chihuahua, this is a Chihuahua. Okay, and so you see that is what we can classify as a catastrophic fail. Another one, and this also is a very current problem that is very much researched now due to the possibility of attacking, so doing a purpose perturbation to classification of deep learning classification, and this is in the paper of Goodfellow and colleagues from 2014. This example is this picture was classified by the system, is an input, and classified as panda with 57.7% of confidence. Okay, and is correctly classified, as you can see. Now, suppose what the authors did was to add this kind of noise multiplied by 0.007, so this is 0.7%. And this noise has the characteristic of being the contrary of the gradient that is used to learn. So basically, if we were training providing this image to the system, and if the system was training, we'd say, okay, 57.7 confidence is not 1, should be 100. So we compute the gradient so that we can improve the classification in the next iteration. So, and the gradient is contrary to the error. And basically what this gradient is representing here is the gradient in the way of the error, so increasing the error. But the system, the authors also provided this image to the system, and it classified this image as a nematode with 8.2% of confidence. Not very good, of course. But when they added both images, it produced this one, and you can see that slight perturbations that you can see here, not very clear, okay, but in some zones you see that you almost don't notice it. And now the system classified the original image plus the perturbation with this epsilon multiplied by the gradient signal, as a given and classified it with 99.3% of confidence. And now I show you what is a nematode, okay? But this doesn't really mean anything because 88.2% of confidence, it's nothing, okay? It's not significant, but this is significant. In fact, it's surprising that the classify confidence, it's here nearly 100%. And we can say, okay, the given has some similarities to the panda, has black eyes around inserted in a white face, etc. But still, the panda was classified with 57.7, and the given, so the perturbed image of the panda is classified as a given with 99.3. So you see, and this happens, why? Well, it's a typical problem of deep learning. Deep learning looks at a large amount of features, and this implies that the sum of small errors in many features results in a large error. And that's precisely what we did here. Basically, we are increasing the errors in every pixel, okay? Only a slight amount, but considering the amount of, these are thousands of pixels here, then we create a large perturbation, meaning a large error. And on the other hand, the identification is done by looking at local characteristics all over the image. So there is a lack of contextual knowledge in deep learning, and that is a problem. And that's something that we don't have because we look at the image as a whole, and sometimes we escape details, but here is the process is the contrary. And in fact, this has led some researchers as Vinograd and Flores in 1987 to state that it has long been recognized that it's much easier to write a program to carry out abstruse formal operations than to capture the common sense of the dog. And this is, they are talking about the symbolic expression of context now instead of looking at details. And actually there is a challenge that was created by Vinograd, it's called the Vinograd Schema Challenge. This is an example that in this phrase in natural language, the trophy would not fit in the brown suitcase because it was too big or small. What was too big or small? Okay, you can do this means that you can do the question with big in both sides or small in both sides. And answer 0 is the trophy, and answer 1 is the suitcase. For us, it's not difficult to analyze that, depending on whether we choose big in the phrasing. If the suitcase is the trophy that is too big, and if you choose small, it's the suitcase that is too small. But this is a very demanding challenge for natural language understanding systems. And it has been favored over Turing tests and stuff like that. And also in subsymbolic contexts or analyzing subsymbolic systems and contexts, this phrase of Joshua Bengio, one of the main researchers in deep learning currently, I'm not saying I want to forget deep learning, but we need to be able to extend it to do things like reasoning, learning causality, and exploring the world. Okay, so basically it's to improve deep models with symbolic context information. Okay, yet we have examples like the Watson by IBM that in 2011 won the Jeopardy game and against 2 human champions, and it used 200 million pages of DBP at the time, WordNet, Iago, etc. 880 cores, 16 terabytes of RAM, etc. And the Jeopardy is a difficult game, even for a human. For instance, these are 3 examples that the computer answered. For instance, wanted for stealing a loaf of bread in Les Miserables, really wanted for other thefts too. So you have to basically the question that is understood is who are we talking about? And the computer answered correctly, Jean Valjean. So the star means in green, it's the correct answer. So it's a character of the Les Miserables, and in fact he was looked for stealing a loaf of bread, but he was an outlaw, and it was really also looked after for wanted for other stealing other objects. And this one is Olympic Oddity, so another theme. A 1976 entrant in the modern. This was kicked out for wiring his EP to score points without touching his foe. And so we're talking about this students who all graduated in the same year, and here it failed because it didn't match the two of them, and chose the first one, and so it chose cheek, and it was class that is coherent for both of them. But you see, there's still quite a good level of understanding, and in fact, IBM created a new division called cognitive computation over this type of software. But currently, in 2022, so a few months ago, Google put out this PALM system, the Pathways Language Model, that used 540 billion parameters model. And the system was trained using 2 pods of 3,072 TPUs of version 4 chips, managed by 768 host computers, and it processed a data set with 780 billion tokens. Okay, and the tokens, so tokens were words in text, were collected from social media conversations in multilingual, filtered web page, multilingual, books in English, GitHub code, so it learned code also, Wikipedia multilingual, and used in English. It took over 1,200 hours of training, and they estimated as taking 3 to 4 teraflops per token of processing. It's described in this Chowdhury and Pirol paper, and it's very interesting indeed. I really recommend. And to see how good is the system now, what can it do? Providing a few examples. So this is called with 2 examples that it is supplied to see, and this is an interpretation of a joke. So the input is the joke. Did you see that Google just hired an eloquent whale for their TPU team? It showed them how to communicate between 2 different pods. And this is the justification of the system. TPUs are a type of computer chip that Google uses for deep learning. A pod is a group of TPUs. A pod is also a group of whales. And the joke is that the whale is able to communicate between 2 groups of whales, but the speaker is pretending that the whale is able to communicate between 2 groups of TPUs. In fact, everything is correct. Maybe in the end, I would just say that the joke is that the speaker is pretending that the whale is able to teach the Google engineers how they should make the TPU pods to communicate. But it's pretty well captured even with this phrase. And another one is in this the input. So Shelley is from Virginia, but he's visiting that city with that famous market where they throw the fish. Going home next Tuesday. Question: is it likely that Shelley will be near the Pacific Ocean this weekend? You see that this is a very complex phrasing and questioning, and needs a lot of culture. For instance, you need to know that the city where the famous market where they throw the fish is Seattle in Washington State. And the Seattle is on the Pacific Ocean. So Shelley is visiting Seattle, so she will be near the Pacific Ocean this weekend. The answer is yes, it is likely that Shelley will be near the Pacific Ocean this weekend. All this was provided by the PALM system. Okay, so it's quite impressive. And I'm closing. I'm reaching the end of my talk, but I want to just close with some examples from nature. And this is a phrase, and actually a paper, the title of a paper by Ronald Brooks in 1980. And he called the paper Elephants Don't Play Chess. But the subsequent phrase would be, nevertheless, no doubt they are intelligent. That's what he defends in the paper. And Moravec, previously in 1998, he defended that symbolic reason demands little computation compared to sensory motor capabilities, which demand significant computation. And the proxy for that, he said, could be the evolution time, or of different species in nature, could be a meaningful indicator. And you see in this schema here that we have the development, first of geology, and then we start having the first bioorganisms, and very simple at first, and then the first vertebrates, and then reptiles, etc., the birds, the mammals, flowers and bees, surprisingly very late. But the primates here, but the Homo sapiens, it's almost, you cannot distinguish it, okay? So all of this reasoning, advanced reasoning that we do, etc., it's very late in species evolution. And so that's why the Moravec defended that capability of moving and surviving in a dynamic world is a necessary base for the development of intelligence. What is called was called by MacLean in 1978 as the reptilian brain, or as Damasio calls it, the proto animals that Damasio clearly assumes that have this kind of autobiographic consciousness, a level of consciousness that the humans also have. Okay. And we have to realize that all natural forms of intelligence physical world, and currently robots and computers have a hard time in perceiving and acting in the real world. That's the main. So in fact, the reasoning is still natural language understanding is still much more impactful than what we can observe in robots and computers acting in the real world. Natural intelligence is also limited, so psychology reveals several experiments of perception failures, of cognition failures, etc. And the animals also have limitations. So there is this very well-known problem of the digging wasp that repeats cycles to put food in the nest for its larvae, for its puppies. It repeats the cycle if the experiment moves the food that the wasp lives at near the entrance of the nest. If the experimenter moves that repeatedly, the wasp keeps doing that, and this was documented by Faber in 1915. And currently, so we see that this context information is, as Christina also pointed out, is one of the hot areas of AI, and actually a lot of research now is focusing hybridization of symbolic knowledge-based systems and sub-symbolic data-based systems, AI. Also another theme is automated machine learning, so automated selection of algorithms adequate to the data set. And you see how important is the context knowledge to detect if this data set requires this type of algorithm or that other. And augmented AI, which is another very important aspect that combines AI with human in symbiosis, and this can be done in a distributed way, like the use of humans over the internet, the workers that, for instance, Amazon has a very popular system for that, for doing that. Okay, all of these try to combine the advantages of, in particular, the augmented AI, the advantages of artificial and of natural, and all of them look at the importance and are evidence of the importance of the context. To close just this slide, manipulation risks. I like to point out that there are manipulation risks by who has the data or who has the technology. Lack of ethics in the design, by the design, or for designers. So that these three types of ethics that Virginia Dignam considers, and in particular in design, there is another important aspect that there is non-ecological AI. And in fact, for instance, that paper that I showed about the palm is very careful in the end, analyzing the energetic balance of the research and of the work, etc. And there is this nice phrase that I also like to use and bring, that is power, the risk of power without enough intelligence, which is not only for artificial systems but also for natural systems. And so what my closing phrase is that AI in context, yes, but we need to look which context for each AI, because in fact, if we consider AI as a tool, then to play chess, we don't need, we just need Deep Blue, or in fact nowadays the sword, the players that we use in the portable computers are enough for that. If we want AI to solve some optimization problem, we need context of the optimization problem. We don't need further context. So for general AI, if we are developing an AI that competes with the humans and represents intelligence similar to the humans, then we would need more context. But in this case, it seems that the lack of this embodiment actuation context might be a strong difficulty for this type of AI. Nevertheless, for instance, in natural language processing, it's been very successful. Okay, and thank you for your attention. I conclude here. I'm open to questions. Christina, your sound, yeah.
Yeah, I put it now. Thank you very much for your very exciting presentation, and I was surprised how you could give us a lecture from the very start of AI to the very hot topics that we are discussing right now, and in the 45 minutes. So thank you very much. I think that I'm going to use it in my classes. It was wonderful. I have two questions for you, and it concerns where your research stands for. So what you are doing right now, in this scenario that you present, specifically concerning inclusion of context in the results. And the second is, why do you think that AI needs embodiment? I think that all the risk or the benefits of AI is like, the risk is like it is in the cloud, so we cannot turn off the AI once we really have it in there. So I know that Google is, there is a branch of research exactly trying to figure out how we can turn off what we created. So might not need embodiment.
No, maybe I didn't explain myself well, but I'm not saying that AI needs embodiment. I'm saying that the type of problems that AI that we can solve with AI may be limited by the fact that we use or not, we don't use embodiment. And what is evident now, we have very impressive results in classification in natural language processing, in game playing, etc., at AI level. But there is no similar, far from that, impressive feat in actuation. And we have robotics, we have visual perception, for instance, is very far from that. So I mean, it's. This was more food for thought that that was my intention in providing this. Well, we should maybe take into account nature that is a very good teacher. Usually, I consider it a good teacher, and see that we may have. It's not criticism in that sense, but it's we can. In fact, there are a hammer is a better tool to put nails, but a screwdriver is a better tool to do screws, right? To screw. So AI, it's a good tool for some things, may not be good for other things, at least in a mid-term future, let's say. The first question, sorry, can you rephrase the first question?
Well, what is your research right now concerning contextual?
Well, actually, my research concerning contextual knowledge is to I'm trying to start some symbolic regression models. It's using genetic programming to produce symbolic expressions that the user can, a human can understand, that describe some type of system, of some type of problem. Usually when we have these sub-symbolic models like neural networks, we cannot go inside. The explanations are poor how the neural network solve the problem. So if we can produce some kind of observation of how the system works with an artificial system, and then use a genetic programming system over it to extract rules or to extract a symbolic expression, an equation, etc., that depending on type of problem, of course, that can be interpreted by the human. I think it's a very positive step towards also the acceptance of these black box models, as they are called, right? Because the fact that we can interpret something gives us some assurance or not, but depending on the type of explanation that is given.
Oh, thank you very much. I'm glad to know that we again are going to be working in some project together, because explanation, Molina too, explanation.
Yes, I think that is
context. So, Francisco, do you have questions for Luis?
Yes, thank you very much, Luis, for your very interesting talk, because you raise a very essential topic, which is the context. But because the context is essential to help an agent, either human or computational, to achieve their goals. So the relationship between the context and the goals of the agent is essential. So I mean, if you want to help the agent to achieve the goals, you need to formalize or to represent the context of this agent in order to help the agent to achieve the goals. So the relationship is essential, even if you then try to represent the context using different techniques, symbolics or neuronal networks or deep learning or whatever. But I don't see explicitly this relationship. And on AI, this has been, for example, with games. The goal in the games is implicit and also explicit, but this is very narrow. And you can represent them, and you can you can also represent or modelize or model the context in order to achieve the goals. But in other areas, like in natural language or in robotics, the modeling of of the goals to the context to help the agent is not as explicit as, or is not as right as or stated as they need. What do you think about that?
It's not as, sorry, it's not as?
No, I think it's not model. For example, in the CIC system, they try to model symbolic everything, but it is, I think it is wrong. And since the beginning, it was wrong because uh, it is better to model concepts situated in the context of the use of this frame. For example, you give the example of the cup. Well, you represented what a cup it is, and if a cup of wine, and if someone is going to drink the cup, well, the representation is completely different. If you want to represent the cup for painting, you don't need to say that if you need to take the cup with your hands, and if you don't take the cup, but if your agent, if your robot is going to use the cup to drink, yes, we need to represent the context and to say, okay, you are going to drink and you are going to move the cup, you need to represent this. And so maybe you need a dynamic representation on the context, uh, taking into account the goal of the use of this context. For example, an animal who is going to to look for food. Well, the context, they need to simplify the context in order to uh, to situate victims and to I don't know, many things, and if the distance, but the goal is to try to catch
Yeah,
or even to run out.
I think I understood now your question now, and I believe that that we agree. Maybe the very last slide, I said that we should use AI context for AI, but depending on precisely on which application, which use are we going to make of the AI. I completely agree with you, but there is, in fact, that maybe I could synthesize the whole presentation. That there is a balance that we need to that we should use. That is the sweet spot between no context at all, or a full context, like the psych system has basically was trying to have, is to have knowledge of everything. Okay, and this is wrong. I agree, unless your purpose is to do abstract research in terms of trying to get knowledge of everything, which is strange for me. But I agree with you. I think, but what I was basically highlighting here is that without context, artificial intelligence is able to reach usually to reach goals that it is posed, but it's much more efficient if it has some context knowledge, and the better the context knowledge it has, the more efficient it gets. And for instance, I think the current deep learning game players, they do it because the context is limited. It's a symbolic context. They can simulate thousands of games per time unit, let's say, and they can play the games, and basically they are discovering from scratch the rules, the heuristics, etc., even if they cannot express them. Okay, so basically they are evolving, they are learning them, which is different from a system that you could provide with, for instance, let's say these 3 heuristics to play chess, and you still have to develop them to say, how do you evaluate the pawn structure, how do you evaluate, so requires some development. But if you could endow an artificial intelligence system, an artificial agent with those heuristics, it would be much more efficient than even the mu0 game players, etc. So I think we agree here. Precisely you need to have a good balance between the context that the agent uses and the goal that you, or the application or the task that it is solving. Yes. But I'm sorry.
Give a chance to our audience.
Sorry?
I want to give a chance to our audience to send you a question. Marisa.
We have a question here. A question from Fernando Dorrier. Given that expensive to maintain an up-to-date context ontology from a human and computer perspective, can we leverage reinforcement learning techniques to automatize context management?
That's a very look. I'm not sure. Actually, reinforcement learning is something that I usually tell my students in machine learning. The reinforcement learning is very useful for agents if you're trying to solve problems where there is an active agent in the world. So if you're solving a game player or a navigator or something like that, where you can have these actions and then afterwards you get reinforcement. For instance, for a classification, for text understanding, natural language understanding, etc., which it's where an ontology would be very useful. I don't really see how reinforcement learning can be a good solution for this type of problems, you see. So for a plain classification problem, plain language understanding, I don't know. If you're talking about a dialogue system, then reinforcement may be relevant, but still it's a very complex and open problem, the dialogue.
Well, when you can lose
okay.
Okay,
I see. So your question was how to to make the ontology more efficient, more contained, let's say. Okay. Yeah. Well, in that case, yes. But it's again, it's something that in this case is not. It's not like you have a goal that you attain, right? It's an ongoing process. I don't see. Do you envisage an ontology that is finished? That's the issue. If it's a general ontology, and that was precisely what Psych was aiming at, is to have common sense. So a general ontology that you can use for anything. As Francisco was saying, the usefulness of it is debatable, to say the least. But that was the goal of Psych, was to have a general ontology that would know everything. I don't know.
The major mistake is like knowledge changes and evolve, and I just want to, since we have many students listening, reinforcement learning, in addition for not being questions that the agent cannot see what is right and wrong, we need to think about the consequence. Can we imagine learning, when you are monitoring a power plant? So you cannot make many mistakes. Each mistake you can, explode the world. So it's kind of, you need to think about the consequences of an error. Trying an error, sometimes.
Yeah, you cannot afford trial and error. Yes, in some cases, exactly. But that's precisely one of the main aspects that that reinforcement learning currently is missing is precisely the magnitude of the errors. Okay, but again, for that you need context information. Usually, if you go to read a textbook of reinforcement learning, they say this is basically a trial and error process. With information that the agent is building a long time, but that's precisely the main difference between animals or humans and an artificial system, an artificial agent using reinforcement learning. If you have to do some actions and meaning, for instance, you have to press a button, okay? You notice, you have several buttons and you press some button and that button is very hot, like it's an oven or something like that, okay? You put the finger and it's very hot, and you don't need too many more experiments so that you learn that you should not put the finger there. But that's precisely one of the problems of reinforcement learning. You can only do that if you have some contextual knowledge. Otherwise, you have always to reflect, well, maybe this happened because there is some stochasticity in my world, because there was someone that was trying to fool me, etc., etc., etc. If you don't have this type of context that can eliminate these doubts, then it's difficult to have a system that can learn in one step, because then it can freeze in a local minimum, let's say. That's the main issue, and I believe that this is due to lack of context of the artificial systems.
Thank you very, very much. Do we have more questions? I think that we are far over our time limit.
Yes, that's true. Sorry for that. I took longer than expected.
No, it was very an exciting topic and very interesting. And you give a tour. You give us a tour of AI. So thank you. Thank you very much for your wonderful presentation. And thank you, Francisco, for being here, Marisa, for sharing this with me. So when is going to be our next meeting, Marisa? Our next presentation?
We don't have the next meeting scheduled yet, but we are hoping the latings in artificial intelligence to talk about the mentoring program that will be held together with Iberamia 22, but we don't have the details yet. We will put all the details in our social media and in the official website of the Iberamia very soon.
Thank you.
Thank you for the invitation. It was my pleasure.
Thank you, Luis. Thank you all. Bye-bye.
Bye-bye.
Cristina, may we talk about